expert interactions, and meaningful deliberations, and across emerging domains of artificial intelligence, data sciences, cybersecurity, and advanced computing technologies. We thank you all for joining us today and hope the sessions ahead will be intellectually stimulating and rewarding.
It is a great privilege and honor to introduce Mr. Kushagra Kakkar, Principal Supply Chain Leader at Amazon USA.
Mr. Kushagra Kakkar is a seasoned industry leader with over 14 years of experience across supply chain operations, product management, and enterprise analytics. At Amazon, he has played a key role in driving large scale transformation, impacting nearly 39 million customers and contributing to over $44 billion in revenue through data driven pricing and operational strategies. He holds an MBA from the University of Maryland Smith School of Business and bachelor's degree in computer science and engineering from Punjab Engineering College. Prior to Amazon, he has held impactful roles at organizations such as Samsung and Microsoft, building a strong foundation that bridges technology, analytics, and business leadership.
At Amazon, Mr. Kakkar oversees workforce planning and optimization for 650 plus sites, impacting approximately 190,000 associates across last mile operations. His responsibilities include developing multi year strategic roadmaps, defining enterprise level metrics, managing critical trade offs across operations, planning, technology, and science teams, and driving scalable solutions that enhance operational flexibility. His work consistently bridges advanced optimization research with real world large scale delivery operations, translating analytical insights into practical high-impact solutions. Now, I request Mr. Kushagra Kakkar to kindly address the gathering. Sir, please.
Hey, good morning, folks, and thank you for that warm introduction. So I'll start sharing my screen. Let me know if everyone can see it and hear me properly. All right, I see it on the camera being displayed. If someone can give me a yes or no if my audio is clear. Can everyone hear me?
Yes, sir, the audio is very clear. You may continue.
All right, perfect. So today, this session is going to be focused on business application of data science. And that real application of tech is what I want to discuss with this audience and walk away with. So what we'll be discussing is the gig economy challenge for workforce availability in platform-based models. So I'm sure some, if not most of the folks here have received a delivery at home from Amazon, maybe within this week. So now what we do not see or have not seen is what happens before that delivery. Before that driver delivers that package in a van, scooter, someone in a warehouse sorts those packages. By that sorting, what we mean is think of it like a super fast post office, guaranteeing your prime delivery within a day or 2 days. And here's the challenge which we will discuss today. So on a random Tuesday, we might need only 100 of these workers to deliver the customer demand. But on December 23rd, before Christmas, which is peak, we might need 400 people. And during those days, we are competing with people from Walmart, Target, UPS, and all other delivery, restaurant delivery platforms for those workers. And unlike drivers who work solo, warehouse workers need to be showing up at specific times to guarantee that delivery time. So today, I'm going to share how we solve one of the toughest problems in last mile through gig economy. How do you predict this flexible warehouse worker staffing when they will show up? How to match the need of customer demand, particularly in economies where there's labor shortage or there's abundance of other opportunities for these folks to work. So let's move on to the next slide. So the gig economy sounds perfect on paper. You have variable demand. Some days are crazy, some are slow. So you hire flexible workers who might come in and out when they're needed. So the problem looks solved, but it is really not solved. Here's what really happens. Um, you're in the middle, like some small size city, middle of nowhere. There are maybe 5,000 people in your area who do gig work. And they're not just working for you, they're working for Uber, Swiggy, stocking shelves at Walmart, Big Mart, wherever. So you're all these retailers are fishing in the same pool to get them reliably to deliver your packages. And unlike rideshare, where a driver can hop online from their couch, warehouse workers required to be physically coming in the warehouse at a specific time. If they don't show up, your packages are late. You miss the delivery promise, and you get an angry customer who starts shopping elsewhere on their phone in a moment's notice. The worst part is you fall in this death spiral. You hire these workers on fixed schedules. They quit because the schedule doesn't fit their lives. You hire the same pool again, they quit again. And in labor constrained markets, in bigger economies, specifically the US, you run out of that pool of people to work. This is what our reality was coming out of COVID. So we needed a fundamentally different approach. Let me make this concrete. We started with what everyone does, right? So what we naturally had in warehouse was fixed schedules. By fixed schedules, I mean you work Monday to Thursday, 8 a.m. to 4 p.m. every week. Seems reasonable, but as I pointed out earlier, demand doesn't work that way. Monday arrives, we planned for 10,000 packages, only 5,000 was the customer demand. Wednesday, we planned 15,000. Uh, Maybe 10,000, maybe 15,000 showed up. So because we have only 50 people coming in and we were planning 10,000, those 15 people, because the demand is not coming in, are just standing around, and that's wasted money. Wednesday rolls in, we planned for 10,000, 15,000 came in. Now our 100 workers are drowning and packages are delayed. So we missed delivery. Even with sophisticated forecasting, we've had some of the best data scientists in the world. Demand is just too variable. Economic conditions, weather impacts, viral TikTok trends, like just creates a very volatile demand. And the there's another problem, right? The best workers, the ones that we want to keep, want flexibility. They're students who can't work during exams, they're parents who need to pick up their kids, retirees who cannot work like 40 hours a week. So fixed schedules push them away. So how we needed to crack the code was dynamically scheduling shifts to match the actual demand reliably. So moving on, here's the framework we built, or the architecture, which I want everyone to like, and we'll go deep step by step into each of these, and how we created models to solve each of these questions. So this is backed by machine learning models, but the logic is very intuitive. So think about ordering food from maybe Swiggy. Swiggy also needs to answer these questions. Will the driver accept your order? Depends on the tip and distance, time of day. How many orders can that driver do? Maybe three, maybe 10. When should they send the order to the drivers? Too early, too late? Which driver would get which order? Matching needs to happen based on location, speed, acceptance, and history. We built the same logic, but for warehouse shifts, and at a much larger and bigger scale. And instead of a one-time order, we were forecasting weeks ahead for thousands of workers across hundreds of locations. So the system has four like interconnected modules and that feed into each other. We'll walk through them. I promise no technical jargon, just business logic in the following slide. So where we'll start is, will they say yes? So we start with the first question: will the associate or the driver pick up that shift? So we analyzed millions of shifts offering through pilots, and here's what jumped out to us. Timing is very important. So if a shift is posted 10 days before, there's a 60% acceptance rate. If it's posted 7 days before, there's a 50% acceptance rate. 4 days, 35, and then 20 to 30. It's very intuitive when you think about your own life, right? If someone asks you 10 days ahead, can you work next Saturday? You can probably plan around it. You can tell your family, you can decline lunch with a friend. But if you are asked on a Wednesday to work a Saturday shift, you've already made plans, maybe for a party, taking your kids out for cricket practice and whatnot. We also found that weekends usually had a higher acceptance, not because people love working, because they had more shifts available on the weekend. So giving more options allowed us to scale more demand. So what we learned, we can't just randomly post shifts. We need to post early to maximize acceptance. We also need to predict demand perfectly that far out. That's the tension we had to resolve. The system learned to predict acceptance probability for every shift, every posting time, every day of the week. It gives you a number. If you post shifts, these many shifts now, you have an X% chance someone accepts. And this becomes a critical input in deciding what shifts to offer. So that's part one. Moving on to part two, how much can they work? This is a critical insight. Just because someone accepts a shift doesn't mean they'll be accepting shifts forever. So we have two types of workers here at Amazon: part time and reduced time. Part time, they work 10 to 20 hours a week, reduced time 20 to 30. And here's what we learned the hard way: these are fixed numbers. The same worker might work 15 hours one week, 25 hours the next week, then 10 hours the following week. Life happens, things happen. Early on, and again, this is a good lesson learned from us. We made a mistake. A worker accepts 5 shifts a week. Great. So we were confident. So we offered them 5 shifts again. Week two, they accepted zero. Why? Personal reason, job exhaustion, and whatnot. So again, this is where we built a capacity prediction model. For each worker, we used to look at their historical percentile. So ranking all associates or all workers from left to right based on their worked hours, we could calculate percentiles. And based on the percentiles, 25th percentile, 50th percentile, 75th percentile, we defined a risk appetite that the business had. 25 conservative, 50th normal, 75th more aggressive. Um, so don't need to rely on any worker, but during peak season, like when we definitely need to deliver the packages on time, we would switch our strategies based on business appetite. So you can't just look at supply and demand in isolation. You need to understand worker appetite. Some workers want tons of hours, some workers want very few. If we treat everyone the same, we will have gaps, and that will impact promised delivery date. So again, the third question we asked was, when do we host these shifts? This is where it gets interesting. We face two opposing forces here. If we post too early, 2 weeks out, where acceptance is high, um, we get higher acceptance. If we post too late, we accommodate to more accurate demand signals, but we lose out on that acceptance. So if we post, but if we So this is where the strategy shift came in, and our realization was we do not need to dump all shifts at once. So our strategy is a mix of both. 2 weeks out, we post a baseline 93%. This is our base load over here. 1 week out, demand forecast improves. We post 1% more to see if more is needed. 3 days out, to fill the gaps, we post the 6%. And one day out is emergency fill if something else broke. I would think of it like airline seat pricing. Airlines don't release all the seats at once. They hold some back, watch demand, and release more strategically to maximize that revenue for them. Um, so that covers question number three. Moving on to question number four. Who gets the shift? Now we bring all of it together to combine all those three models around acceptance, shift release, and capacity prediction. And those are our supply equation, and we marry it up to the demand to come up who to uh, uh, who to offer these shifts. Think of it like Tetris. So here we are juggling 15 different types of shifts, 4 hours, 8 hours. We have 200 flexible workers at the warehouse, each with their own acceptance pattern. We have hourly demand curve, which looks kind of like a sine curve. We know that acceptance probability of each shift. We know each worker's weekly hour. So the system now creates an optimal mix of shift postings. Um, and those shift postings fills our demand while maximizing the chance of workers to accept. This is where reliability comes in. So based on these three models, based on the demand, we recommend the shifts based on that demand, which have a high probability of getting accepted. Um, I can take an example. So Monday, 8 a.m. to 12 p.m., need 50 workers, post full shift, have a high acceptance of 65%. Wednesday, 2 to 4, 20 workers, pick and stage, or like the second shift, acceptance 55%. So don't post Thursday shifts, already covered, no demand. So that is how the output flows out from these capacity system models, all of them based on historical data, machine learning, marrying it up with the demand to spit out those outputs. So the results, what did we see? Reliability jump 93%. Um, this is a very important metric for Amazon last mile delivery. The percentage of shifts we planned for that actually got filled. So before having this model, we were at 78%, meaning 22% of the times we were not able to deliver on time. And we were using methods like surging high demand premiums chronically and incurring more revenue. Packages sat at the warehouse, so that's bad. After implementing this, 93%, which is very much comparable to our fixed schedule workers, which sit at 97%. So it's roughly only 4% off. Um, Scale, we went from because of this, we went from 5 to 25% now. That's a 25x increase in flex capacity. Now, this flex capacity can flex up and down and absorb the demand shocks that we talked about earlier, and causes us to be more nimble, not have hiring spurts, and just have overall more fluid and flexible operations. Um, Cost, I'll talk about. We reduced wasted capacity, times we are paying workers but don't have work for them by 700 basis points in the network. That's a lot of revenue saved. We are winning the talent war. Remember the problem where we keep hiring, losing the same workers? We cracked it. We are offering flexible schedules that fits workers' lives. Students can work around their classes, parents can work. Workers are happier, attrition is down, and given people control over their schedule has been a big win in the last 2 years when we've scaled this workforce. So moving on, like I'll cover the key lessons learned. I think we talked about them. Uh, Timing decay is real. I showed you earlier that acceptance drops 60% to 20% as you guys get closer. We didn't just learn this intellectually. We felt it in the data, right? We failed multiple times, and that's how we adjusted our posting horizon. We tried posting 3 days out, more accurate forecast, acceptance tanked. Promised delivery dates got pushed. Weekend doesn't seem equal to weekday. That's another lesson we learned. Capacity guardrails are essential. So we have to. Now, I talked about flexing up and down the hours for these associates based on demand. But in order to keep them engaged, you need to constantly offer them a minimum amount so that you know they're still working for Amazon or are still engaged on coming in. So that's something we learned, adjusted our models, put those guardrails in. The fourth one is very important. Trust is earned, not given. When we first launched, managers overrode, or like the on-field operations team overrode 61% of the system's recommendation. It's a big number. They did not trust the black box. We had to constantly show them, look, when you overrode, here's what happened on acceptance rate, here's what happens to cost. Over time, with proof points, dropped capacity, and with the advent of agentic AI to address all of these questions real time, now the system is more trusted. But you have to earn that trust through transparency and results and constant communication. Um, integration, like most of the systems need to have a more on-time dynamic. All systems need to be integrated. You can't have this in isolation. Um, the meta lesson learned, I leave this like operational complexity is where a real challenge lives. The algorithms are hard, yes, but driving change, system integration, and earning trust with on-field people who are actually doing that's harder. That's definitely harder. So how to apply this mental model everywhere else, right? So we talked about how Amazon did it, but the good news is this framework is transfers to any platform-based model, any business model. So rideshare, where drivers accept rides, depends on distance, surge pricing, time of day, how many rides per hour, traffic location, when to send the request. Too early, driver isn't nearby yet. Match the driver to which rider, optimize wait times and driver efficacy. So rideshare, healthcare, restaurants, retail, wherever you have a gig economy and you're trying to wow workers to come work for you, uh, you can apply by asking these four questions. Um, so I hope that this is informative for the group. What we need to start implementing this to a gig economy is nothing but collect historical data. You need at least, I believe, 3 to 6 months of data. How to post, who accepted, who showed up, and actual demand. Find the patterns, use basic analytics to get a start, make scatter plots, obvious trends, and then test the hypothesis. Right? When can you be reliable? Weekend, weekday, experienced workers, what shifts are getting easier to fill, what timings are, what customer demand is actually real and that you can fulfill. Think of it like if you figure out these are the most um, frequently ordered items, then you can build your models around that. And then you earn trust gradually, of course. This isn't theoretical, it's just tested at massive scales across hundreds of locations and thousands of workers. Uh, and the principles transfer to any gig economy. So with that, I'll go on to the final slide and open it up for Q&A. I have a brief summary which we can look at and walk through, but let's open it up for Q&A now.
Thank you very much, sir, for the insightful address. We have time for a few questions from the audience, if you'd be kind enough to take them.
For sure.
Thank you, sir. We have questions. Just a minute, sir.
My question to you is, what was your thought process when developing this research, and what measures you took to differentiate your work from other similar works?
Oh, I think the challenge for us, especially during, that's a great question. Thank you for asking. So the need for this to happen was particularly during the COVID times, where customer demand became very sporadic or volatile. There were periods when it was very high. There were periods when it was very low, and we were not staffed to flex up to absorb that customer demand, and we were losing business to other retail partners such as Walmart. So that's the need part. How did we differentiate from other areas? I think where it becomes challenging or is not comparable to other models is the reliability portion and predicting 3 to 4 weeks out. So right now, if you think of like business models such as Swiggy or what, you order a drink or a food package on those applications, they get you that information in real time and are able to surge or up the demand on real time and get you that within 20 to 30 minutes. Now, the problem becomes much more difficult in areas such as the US, where we don't have those many workers, and we need to predict this demand 3 to 4 weeks out. Um, we don't know if people will pick them up If they pick it up, we are able to guarantee that capacity. What happens when we move closer, if volume goes up or down? So those are places where we tried, tested this architecture. And I'll move back to this architecture. I think this is pretty telling. This architecture wasn't built in like 1 month, 2 months. It took us an iteration of 6 months to a 1 year to build this. Looks simple enough, but acceptance probability is something we learned about by trying and failing. Shift releasing is something we learned about with trying and failing. And over time, we've been able to build trust to actually expand this. Hopefully, that answers your question. If not, I can clarify more.
Thank you, sir. That answers my question.
Okay, so we have one last question for you. What were some challenges you faced when conducting your research?
Okay, I think the challenge is getting good data when it's a start, because people are very even though it looks good on paper, it's very difficult to actually get the data to to make reliable recommendations. So that trust portion of relying on a data backed model to actually get used in field was the most challenging part of our journey. What we learned was getting that trust takes time, takes transparency, and takes a lot of um, hand holding to become hands off the wheel. Um, all of these models that I've talked about, acceptance probability, shift releasing, capacity prediction, there is a key challenge to machine learning and machine learning or like regression learning models. The operator or the user will always feel that they know more than the black box. And that's where the most of the challenge came. So what we've done over time is build agentic solutions that describe the model on why it is predicting acceptance probability the way it is, releasing shifts the way it is, and given the user an opportunity to override these prediction models within certain guardrails based on their risk appetite. That skin in the game, or those guardrails and that explainability has helped us earn trust and scale it faster from 5% to 25%.
Okay, sir. Thank you, sir. That answers my question. Okay, sir. Thank you very much, sir, for such an insightful and engaging address. Your perspectives on large-scale supply chain optimization and data-driven decision-making have offered valuable industry insights to all of us. Thank you again, sir.
Thank you.
Ladies and gentlemen, we shall now move ahead with the next scheduled segment of the conference.
It is a great privilege and honor to introduce Professor Dr. Banani Roy, Professor and Director of the Interactive Software Engineering and Analytics Lab of Department of Computer Science, University of Saskatchewan, Canada. Professor Dr. Banani Roy has received her PhD from Queen's University, Canada, in the area of interactive software engineering and is a distinguished academician and researcher in the field of software analytics and interactive software engineering. She is a co-applicant of the NSERC CREATE program on software analytics research, SOAR, and has been actively involved in two Canada First Research Excellence Fund, CREF projects, contributing significantly to advancing research in human-centric software development and innovation.
Her research focuses on supporting multidisciplinary data analytics and software analytics to develop human centered tools and techniques for reliable, scalable, sustainable, and cost effective software development, maintenance, and evolution. Through her projects, Professor Roy has worked with over 20 graduate and undergraduate students, producing high quality research publications and earning multiple prestigious research awards. These include Best Paper Awards, Best Poster Awards, Research Excellence Awards, MSc and PhD, Geddes Awards, MSc and PhD, and 75th Anniversary Scholarships PhD, among others. She is also actively involved in the global research community through conference organization roles, most recently serving as program co chair of SCAM 2022 and general chair of IWSC 2023.
Now I request Dr. Banani Roy to kindly address the gathering on the topic leveraging LLMs for program comprehension and knowledge transfer. Ma'am, please.
Okay, I'm going to share my slides. Okay, can you see my slides?
Yes, ma'am, it's visible.
And am I audible?
Yes, ma'am, you're audible. Please go ahead.
Okay. Hello, everyone. Thank you for the nice introduction. Yeah, I'm Banani Roy. The title of my today's talk is on leveraging large language models for program comprehension and knowledge transfer. So you already introduced me. Here I put a slide about me. You can see some of my students like who are doing PhD, masters and postdocs with me. Many of my students have already graduated and my research interests include software maintenance and evolution, software renovation, mining software repository, and also like I work on engineering scientific workflow management systems for big data analytics. But my today's work is focusing on program comprehension. So program comprehension is about understanding the source code of a software system. And it's a very important task nowadays because the code base is increasing. The lines of codes are huge nowadays, and we are also having a lot of open source software developments. So here you can see the ratio of reading versus writing code is 10:1. Developers spend huge amount of time for solving issues caused by other developers, onboarding a new when new developers join to a project, they spend a lot of time to onboard with the software system. And as you can see, 100 million developers currently on GitHub. So GitHub users are increasing exponentially over the time because of this open source development practice, and about 2 billion contributors in the GitHub as of 2022. So many open source software systems and people are contributing, and they need to understand code base. So in my lab, we do different kinds of work for program comprehension. We try to understand code base in a different way. So one way is code summarization, where we try to generate inline comments using LLMs. We also generate method level comments for the code. And as you can see, we also publish papers and we also try to like understand code base by offering technique where developers can navigate the code base using high level code summary tree. and we also work on how we can actually help new developers to learn from the expert developers by knowledge acquisition and transfer. So I will try to cover some of the techniques today. I might not able to cover all the techniques, but I will give some overviews due to the interest of time. So what is a method level comment? You all know, I'm sure. So it is a doc string. So in a method, you can see like a summary of the comment, then input, output parameters, description. And what is inline comments? So inline comments are generated like beside a statement and talks about the purpose or some kind of intention of the statement. So here I gave 2 examples. So so that you guys understand what I'm talking about, what is method level comment and what is inline comments. So the task here is to like generate natural language description that explains the functionality of the code. So here you can see here is a method. It's called calculate n top bound. So when you generate the summary of the method, it the natural language text looks like that. Calculates the resulting y coordinate of the view's top bound based on the y position of the view and the y axis delta. So this can help developers to understand the code in a natural way, and which enables easier program comprehension and software maintenance. But now the question comes like how we can generate the comments automatically, and what is the state of the art research, and what is the scope for improvement. So if we use kind of pre-trained model like CodeBird for comment generation, for example, for this method like void close, it closes the connection. And there is one state of the art technique, it is called ASAP. It used kind of prompt based technique like GPT-4 to generate comment, and which uses kind of code search net data set as to fine tune. But the thing is that as you can see, the generated comment by CodeBird or ASAP varies a lot from the like human developers comment. It actually cannot express the like functionality of the method naturally and properly. So as you can see the difference, so the state of the art solution is not perfect, and there is some scope for improvement. So what is the problem here? The problem here is that the current solution doesn't consider the context, in the method properly. So how we can define the context here? For example, when you are writing a method, the method also contains some helper method inside. So in order to support reusability and modularity, like when you write a method, it actually calls other method inside it. And when the existing techniques generate comments, it cannot consider these, it doesn't consider the helper method as context. And the method which is calling these helper method called dependent method, and there are some method which actually doesn't call any other method, it is called independent method. For example, here add is a method that is independent method because inside it doesn't call any helper method. But close is a method which actually is a dependent method that calls the helper method await clause. So the based on this, like what we did, we actually propose help.com that utilizes helper methods to generate meaningful code comments. So when LLM is generating comments, we are telling the LLM that you also need to consider the helper method in your context. So we worked on 3 research questions based on these helper method context. So first we wanted to verify the importance of dependent method in open source projects. So the first research question was, to what extent does the evolution of dependent and independent methods vary in open source projects? Then we also wanted to check, like, how do existing approaches, like I was talking about CodeBird and ASAP, perform in generating comments for dependent method compared to independent methods. So whether like they are considering any dependent method when they're generating comments, or they are just considering independent methods. Then research question 3 was, to what extent does leveraging helper methods lead to the generation of higher quality comments for dependent methods? Now, if we consider helper methods, whether it is improving the comment quality or not. So here is our methodology overview. So what we did, we took projects from GitHub, then we used tree sitter to extract methods from the project, then save it to database. Then we fetch method history, and here we with that each method, like we try to include all the helper methods inside the dependent method. So here insert is a dependent method, then inside there are 2 helper methods, shift up and grow. So we created a database, then we designed a prompt. So in the prompt we are telling the LLMs write down only the summary part of the Java doc comment that would have been written by a developer for the following method. So this is the method we are asking to generate comment, but we are also giving the context like the helper method body as the context. So this is the prompt we are using for generating method level comment. Then we are doing automatic evaluation and quality check via survey. So for our automatic evaluation, we used semantic and syntactic metrics. I'll talk about this soon. But first, let's see for research question 1, like how much dependent methods and independent methods are prevalent in the open source projects. So here you see we consider 10 Java projects which have 648K methods, and among them we have found 70% methods are dependent methods. So most of the methods are dependent methods which use helper methods, and we also see that dependent methods actually that like involves more commits, it change prone, and it involves higher author engagement. So which indicated that we really need to pay attention to generate good comments for the dependent method. Okay. So now after research question 1, we compared that, if we generate comments when we ran the baselines over our data set, like the baselines like code T5, code BERT in our data set, what is the matrix value comes. So we calculated the overall matrix score, combining the syntactic similarity and the semantic similarity. I'm sure you know about these matrix, BU, BLEU, Meterator, Rogel, which are syntactic similarity matrix, and semantic, like which sees only the meaning of the comment. So these are state of the art metrics for evaluating comments. Then we saw that the scores, overall scores for the baselines like code T5 and code BERT are actually very low, and whereas in literature they have higher value. So then the question comes, does method type affect more model performance? So like what type of method they have considered here to generate the comment. Then we compared like the matrix values between independent and independent method. So we found that most of the cases, the independent method got a higher score than the dependent method. So for almost all cases, independent methods scores are higher, 7 to 13%. So we need actually better approach for dependent methods. So in order to do that, so we applied then the context independent the helper methods in the context for generating the comment, and we have a level from 1 to n level. So we figured out that the improvement in the matrix, as you can see, different matrix, the OMS overall matrix scores increased from 5 to 50% improvement. So here you can see some qualitative analysis. When we used code BERT summary, code T5, SUP, and helpcom summary. So the ground truth, the reference comment mostly matched with the helpcom summary, and here helpcom summary, it actually considered generating the helper method information inside the comment summary. Then we did some survey for quality checking, and we got 162 survey responses, and our survey was ethically approved. And we asked the 3 tasks, and each having 3 like program comprehension tasks. The participants comprehend 3 code snippets, like 3 methods with and without helper method, and most of the cases, like 75%, 75% participant actually chose helpcom's solution. So actually they didn't know what kind of comment they are choosing, but later we figured out that helpcom was preferred by most of the practitioners. So here there are a lot of research implications for researchers. So helpcom's performance open up new doors in research, we should explore more ways to utilize dependencies for better program comprehension. So when you are generating comments for a method, it's really important, like what other methods are involved there, and so dependencies are important. Um, and for software maintainers, have to be careful while choosing an ideal tool for comment generation. And should focus on selecting tools that prioritize semantic meaning. So we showed that different types of matrix score, which involves semantic and syntactic matrix, but software maintainers should consider on semantic meaning. And for novice developers, using automated tools may be tricky for a beginner. Developer should actually choose kind of expert opinions in case of confusion, because all the times the tool they will choose might not give the good summary, as we can see. But if they don't see good summary, they should seek expert opinions. So there are some threats to validity, but I'm not going to talk about this due to lack of time. I'll move on. Another interesting work we are doing, adaptive code summarization. The idea is that the current approach is all the comment generation techniques generate one general comment for a method. It is kind of one size fits all comment generation technique. But in real life, developers are of different expertise. Some are novice, some are very experts. And novice developer may find a comment useful for his understanding that may not be well appreciated by an experienced developer. So here in this figure, you can see that the novice developers wants to see detailed comment, whereas expert developers want to see concise comment. Now, how we can generate comments depending on the experience of the developers. So on this research, we are working on 3 research questions. So here is the 3 research question. What are practitioners' expectations for code summarization when considering varying levels of expertise? So does practitioners need the necessity of generating different types of comments for novice or versus expert developers? Can we design and adopt a strategy that generates code summaries tailored to developer expertise? And how effective is the proposed approach when integrated into a real-world environment, such as VS Code's Copilot chat? So with this research, we are trying to answer 3 questions, and in our methodology, we are actually, here is the methodology. We are reading a different literature to see like how they talk about this experience level for generating comments. Then based on our findings, we created the prompt template, and we used our data set that considers the helper methods and the method. Then we used GPT-4 Llama, and then we generated the comment based on our prompt. So here in research question 1, practitioner expectation. So these are the findings that we got from literature. These findings show some differences in comment intent,
Hello?
length, and pattern. Yeah.
Excuse me, ma'am.
Yes.
Kindly wind up the session as the another speaker is waiting.
Yeah, I have 30 minutes, right?
Please wind up.
Yeah, so I have still 7 minutes to go. And expert developers, you can see. So here you can see that experience the literature shows that expert developers want to see comments with intent, but novice developers with like detail. So all those things we empirically validated. Then we come up with the prompt, and we decided that length of the novice prompt should be 2 to 3 lines. Then intent summary should explain the method from what, how, and why, focus on parameters. And then we wrote all these prompts that are for novice and expert. Then we actually see the effectiveness of our approach. And in this case, you see that which novice-oriented summaries are better than the expert ones when compared against HelpCom. These results show that adaptive summarization is possible without compromising quality. Then we try to integrate in the real world, like with here is an overview of how we can generate a summary of a single method. So we integrated the prompt in the Copilot chat, and then we asked the developers whether they like this kind of thing. And we got promising results. So we are doing also a lot of other research with inline comments, but I will summarize because due to lack of time, as I was saying, I might not able to talk about this, but in conclusion, actually what I want to say, we are leveraging LLMs for different software engineering tasks. One of them is program comprehension, and when we are considering program comprehension, we need to do a summary of the code, and one is method level comment generation, inline comment generation, and we are also working on explaining bug detection models output in the ID using explainable techniques, which actually leverage program comprehension. And we are using also different human-centric approach where we can actually save the comprehension experience of the developers, of the expert developers, and we can transfer it to the novice developers so that they can later see how actually expert developers try to understand the code, and how they explain the code using summaries. Yeah, that's it. Thank you. If you have any question, you can ask. Yeah.
Thank you very much, ma'am, for the insightful address. We have a couple of brief questions for you, if you would be kind enough to take them.
Sure.
Ma'am, I wanted to ask, what are the main challenges that are faced in using the large language models effectively?
Yeah, that's a pretty good question. So main challenge was the creation of the dataset. So we had to work with a lot of methods and helper methods. The existing dataset code searchnet didn't actually give us the right data set. So we needed to work on a lot of projects and extract the methods and make our data set. Then another challenge was to work with a lot of metrics and figuring out how these metrics are suitable for comparing the baselines. Yeah.
Thank you, ma'am. That answers my question.
All
Yeah,
right. Thank you very much, ma'am, for such an insightful and engaging address. Your perspectives on leveraging large language models for program comprehension and knowledge transfer have provided valuable insights for researchers, practitioners, and students alike. Thank you so much.
Thanks.
We conclude this session scheduled for this segment. On behalf of Amity University, Uttar Pradesh, we extend our sincere thanks to all esteemed speakers, session chairs, faculty members, and participants for their valuable time and contributions. Thank you.
Thank you.
Thank you, ma'am. 6DS1, 6DS2, kindly move to E2 SEM hall. DS1. And IoT third year, IoT second year, you will gather again in E2OD 3 to 5. Whoever attendance is pending, kindly discuss. Thank you, ma'am, for the nice session. Your research is very wonderful.
Okay, thank
I
you.
will continue with you after my session so that I can discuss your research in more detail. Thank you
Yeah.
for guiding
Yeah,
us.
thank you for giving me the opportunity, and thanks to Dr. Gorima, yeah, for inviting me. Yeah, please convey my thanks to her. Yeah.
IoT1, please stay. Attendance will be taken again.